All right, so welcome back from break. Before we left for the spring break, we were covering lists and list-based data structures. We covered why arrays, just plain old arrays, are bad. And then we went through a design, an implementation, and testing of an array-based list. You've been using array lists in Java for the entire semester, but we went ahead and we looked at how you would actually design that from scratch. We also identified some secondary functionality that would be nice to have, other than the basic CRUD, that is put stuff in, create stuff, retrieve stuff from the list, update stuff, and destroy, in other words, remove stuff from the list. Now, just to remind ourselves of what it looks like, let me come over here, and this is our demo where we're putting a bunch of stuff in here. But let's go ahead and take a look at the actual list here. Right? We have an underlying array here that is a bunch of integers. And then we also keep track of the size, because the size of the array is not the size of the list. That's the capacity of the list. And initially, we set it equal to 10 here, that they can hold up to 10 elements. When it got full enough, we called this other function that expanded the list and increased the size of the array by creating a new array, copying everything over into that new large array. We have an add element to the end of the list function. We have an add element to an arbitrary index. Right? And remember the basic steps for all of these index-based methods that we did is that we check the indices, right, first. And then we check to see if we should expand it or not. And then we copy elements over, or we shift elements over to make room for it wherever it is. We place X at that index, and then of course we keep track of the size because we've added something. The size goes up by 1. We have a retrieval method here. Again, the basic steps are you check the indices, see if they're valid, and then move forward if they are. Otherwise, you throw an exception. We have an update element, all right, that basically does, again, the same checks, and then it replaces the element and returns the element that you just kicked out of the list. A remove element, and a couple of other helper methods down here. The helper methods we made all private. Why? Because we don't want to have a leaky abstraction. We don't want to leak information to the outside world about how this list is actually working. Okay? So there's our little bit of a review of what we had done so far. But what I want to do is a little bit of an improvement here. Right? What is my integer array list good for? Only integers, right? If I wanted to do this for doubles, I would cut and paste that entire class, change every single instance that I have int, I would change that to a double. What if I wanted it for strings? Same process, I would cut and paste and then change all that to strings, right? Instead, what do I want to do? I don't want to do that. I don't want to have a list for every single type. I want to have one list to rule them all. Now, if you go back all the way to Lab 5, you did this. It was called generics. It was called parameterization. So what I'm going to do is I'm going to make a copy of this because I want the old one to compare it to. Let me go ahead and create a new copy here. And the copy is not going to be integer array list. Instead, it's going to be my array list. I don't want to call it array list because I don't want to confuse it with the one built into Java. Right? And let's go ahead and open that up and see how we can modify this so that we can make it generic to apply to any type. Remember the way that you did this in Lab 5 was by making it into a parameterized class. Now this class is parameterized to types of elements of type T. Right? What is a T? Well, it could be an integer, it could be a double, it could be a string, it could be whatever you want it to be. It no longer holds just integers, it holds elements of any type. Okay? All right, well, what changes based on that? Well, again, we're no longer holding integers here. We're holding elements of type, not doubles, not strings, but what elements of type are we holding? What are the type of elements that we're holding now? T, right? Okay. Well, there's a trick here, right? I can't create an array of elements of integers and expect it to hold anything. So I'm going to go ahead and create an array of elements of type T. Now, unfortunately, I can't do that, and that's because there's a little bit of history quirk here with Java. That generics, in other words, parameterization, those were introduced in Java 5, right? There had been 4 versions of Java without generics at all. And in order to accommodate those older versions, what we have to do is we have to make this into a generic object. In Java, everything is an object or belongs to an object. In this case, I can create an array of objects. The reason that I have to do this is because if I were to create an array of integers, the compiler knows how many bytes each integer takes. 4 bytes. So 4 times 10, okay, here, you want 40 bytes. If I were to change this to a double actually takes 8 bytes. So 8 times 10, here's your 80 bytes. Right? If it's an element of type T, I don't know what it is, so I don't know how many bytes it takes. But if it's a generic element of type object, I do know how many bytes each object takes. It's only, I think it's 8, right? Because it's actually not the object itself, it's a reference to the object. It's a pointer to the object, basically. Now, ARR is an array of elements of type T. I've created an array of elements of type object. So I need to force those objects to become elements of type T by using a typecast like this. And this is unfortunately how you have to do it because of the history of Java. Java didn't have generics at first, and so the way that they introduced them was through something called type erasure that we won't get into. But basically, this is how you have to deal with it, right? In order to make all your code backwards compatible, right? Okay? All right, so what else changes? Well, I'm no longer adding an element of an integer to the list. What am I adding to the list now? An element of type T. Right? Adds the given element at the index specified. Again, we're not adding elements of integers. I'm adding elements of type T. Right? And the compiler error that was up there before goes away because I'm passing an element of type T now. Does anything else change in this entire function, in this entire method? Nothing. Right? It's all exactly the same. So let's keep moving here. All right, well, if I get an element at a particular index, it's not necessarily going to be an integer. It's going to be an element of type T. There we go. And that compiler error goes away. It replaces the element of a type of integer and returns an element of type T. Right? That also means that my local variable here remember I'm replacing it, so I put it into a temporary variable over here so I can overwrite it and I can eventually return that temporary variable. That's also an element of type T. Right? There we go. Save it and it'll compile there. If I remove an element and return it, then it's going to be of type T. And the temporary variable, again, needs to be an element of type T. Right? We decrease the size, et cetera, right? Expand, I don't think I need an explicit typecast here, but that's because arrays.copyOf, I believe, was introduced in a later version of Java, and so it is actually returning a parameterized version of itself. Otherwise, there's nothing else that needs to change in the entire thing, right? Now, what have I done by simply erasing the types of elements of integer and making it of type T? I've created one list that can hold any type at all. The current types that you know of, but any future types that you would introduce into the language, like say a service or a contract or something like that in your project, right? I don't have, this is awesome. Now I only have to have one implementation and it can apply to many, many types. This is polymorphism in action, right? Let me drive home the point that all you have to do is change integer to T by comparing these two files now. You can do this in Eclipse by highlighting them and then right-clicking on them, and then you can compare with each other. And let me expand this so that, come on. There we go. And it's basically doing a get diff kind of between these two things. Ignoring the white space here. In fact, is it already ignoring white space? Nope. Let's go ahead and ignore the white space if there's any, right? Differences. And other than the name, and any time that you say it has an integer and it was replaced with elements of type T, none of this code has changed at all, right? In fact, I intentionally wrote the documentation generically so that I wasn't making reference to any integers, and I didn't have to change any of that as well, right? All right, great. That means that I've solved this problem once and for all, right? That I don't have to have an array list for integers, an array list for strings, an array list for contracts, et cetera, et cetera. I just have one array list. Now, what does it look like over here in the demo class to do this, to actually do this? it would now be my array list, right? And I would make it for, in this case, I'm adding integers, so I would parameterize it to an integer. Now, all those instances where I had t in my array list class, they would now get replaced with integer by the compiler, right? And I would also parameterize the call to the constructor there, right? Otherwise, nothing else needs to change here. And I can also change it so that I can have another list here, bar, right? Call it bar. That is not for integers, but instead for strings, right? And I can say bar dot add element, hello, right? And bar dot add element. We'll add world. What we'll do is we'll add a different index here at 0. There. Okay. So I now have one implementation, and I don't ever have to reconsider this implementation ever again. Okay. So my answer to the original question here was, what is that good for? It's only good for integers, which is bad. But now, what is my integer array list? My array list good for? It's good for everything, which is much, much better. Right? Again, polymorphism in action. Okay. Now there's still a problem over here, and the problem happens when you try to insert a lot of elements. 1 million elements, is that a lot of data? So these are all integers. So 1 million integers, that's less than 4 megabytes. Would you consider that big data in 2026? No. But at least it's quick if I add them all at the end, right? Let me go ahead and starting. Actually, it's not that quick. Let's go ahead but that's because I'm doing a lot of other stuff on my computer right now. There we go. So let's go into that class again, and let's change this to, I don't know, 1,000. There we go. Now let's come back over here and do our test again. Right, now it'll expand every 1,000 or so. It should be done in a couple of seconds here. Again, it's artificially slow here because I've got a million things running for the presentation purposes. There we go, it's done, right? But now what if I change one small thing? Instead of adding it to the end all the time, I'm going to add it to the beginning every single time, right? Now that did take a couple of seconds, so let's go ahead and be patient, and maybe it'll still take a couple of seconds here. What do you think though? Will this just take a couple of seconds? Or will this take a couple of minutes? Hours? Hours turn into days, days turn into weeks, weeks turn into years. Now we're talking. This will probably not execute in the next couple of years, maybe 20 years or so. I don't know. But why? While that's running, let's come over here and understand what happens every single time. So suppose that I just run into, that halfway through this. Suppose that there are n elements in my array list right now, right? And I want to insert at the very beginning here, insert at index 0. What do I have to do to make room for it? I have to take all these elements and shift them down so that I have a place to put that element, right? Now when n is small, right, say there's 0 elements, then the number of shifts is also small. I don't have to shift anything if there's no element in it. But if there's one element, then I have to move that element down, right? And so there's one shift. If there are 2 elements in there, I've got to shift that one, and then I've got to shift that one over, and so there are 2 shifts there, right? And you start to see a pattern here, ... If there are 500,000 elements in there, then how many shifts do I have to do? 500,000, right? At the end, when I have 1 million elements, then I'm going to have to shift over 1 million times, right? Now this is cumulative. What if I were to sum all of these up? What's the sum of all of these, right? 0 plus 1 plus 2 plus 3 plus 4, all the way up to 1 million. You may or may not be familiar with this, but the sum of natural numbers of 1 plus 2 plus 3 plus 4 plus dot 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 plus n. This has a closed form solution due to Gauss. Remember Gaussian elimination, Gaussian distribution, the normal distribution, etc. Big time mathematician, right? Then it's going to be like this. N times n plus 1 all over 2. Right? And if you're taking 235 right now and you eventually get to induction, if you haven't done induction already, then this is probably going to be the first inductive proof that you see. That you're going to show that this summation here is equal to this closed form solution over here, and you'll do it using induction. Right? Now, what if n is equal to 1 million, as it is over here in my example that's still running, by the way, right? Is it still running? Yep, right? And it will be running for quite a while, right? Then what if n is equal to 1 million? Then that's 1 million times 1 million minus 1 all over 2. Right? So now the two largest values here are going to be 1 million times 1 million. What's 1 million 1 millions? If we don't know that, then that's okay. We can ask. Let's go to, come on, Wolfram Alpha. All right. So, I think you can do it like this, times 1 million minus 1 all over 2. Right? How big is that? M is a variable. Okay, it's going to be, interpret that as a variable. How do I get 1 million? That's going to be 10 to the 6th. All right? 10 to the 6th. So how big is that? That's about 500 something, 500 billion, right? Now suppose that now let's just take a typical desktop computer here and say that you can do 10 million operations per second here, right? 10 million shift operations per second. That's going to be divided by 10 to the, now 10 million is going to be 10 to the 7th, right? What's that going to be? Decimal form. That's going to be 50,000 seconds, right? So let's go ahead and convert that. 50,000, 1, 2, 3, seconds to hours, right? That's 14 hours right there, right? And that's assuming that you can do, what did I say, 10 million operations per second, something like that. Even if you went 10 times faster, then it's still going to be 1.5 hours. If you went 100 times faster, it's still going to be like a quarter of an hour, right? So should I even bother letting this run? No. The problem was that we were always shifting stuff. Is there a different type of list that I could insert something at the beginning without having to do so much work, so much heavy lifting of taking these 1 million elements and shifting them down to make room for that? And that's going to be our next topic of discussion here. They're called linked lists. All right? With a linked list, there is no underlying array. Instead, elements are stored inside these things called nodes. All right? Each node consists of an element and a reference to the next node. All right? So it contains, a node is going to contain these two things. All right? Let me show you visually what it looks like. Okay? So a node I'm going to depict here as a box. And the two things that are in that node are the elements. So let's just go ahead and say that we're storing 10 here. Right? Again, we'll go with integers. And then this is going to be a reference to the next node. Right? And this is next. Right? That's going to be another node. Let's say that there's 20 stored in there. And then that's going to be a reference to the next node. And we'll say that 30 is stored in there, et cetera, dot, dot, dot. Right? Well, it's got to have some end at some point, right? So let's just suppose that the last element here is going to be 100. There we go. How do we denote that we are at the end of the list here? Instead of pointing to another node, it's going to point to some special value, right? Which I will denote as phi here. Now, in practice, we're going to have to, of course, define what this means. This could be null, right? Because we're working in Java. How do you define something that doesn't exist in Java? Well, the null pointer does that. Right? We also have to have a beginning. Okay. So what we're going to call this beginning is the head of the list, right? Just like the head of the line, right? And then this is this last one here. This is called the tail, right? Because of course, if you have the head, then at the end you're going to have the tail. Okay. All right, great. Then what would I do in order to add an element to the beginning of the list here? So add at index, and I'll put index here in quotation marks here, because there's actually no indexing here, right? But I can still use the same concept. We'll add it at index 0. What would I have to do? Step 1, create a new node, right? So suppose that I've created that node here, and oh, come on, that's an ugly one. Need to close my gap there. Come on, there we go. 42, okay? Now initially 42 is pointing to null, right? Because I just created it, okay? 2, what would I do to add it to the beginning of the list? I would make the new node refer or point to the head. Well, what would that look like? The way what that would look like is I'm going to go ahead and take this. Where's my grab tool? Ah, they updated it? Okay, there we go. There it is. And I'm simply going to make it move up here. Right, there we go. Now 3, is this still the head of my list if there's an element over here? Nope. So what I'm going to do is I'm going to update the head reference so that you are pointing to the new node. So that means I'm just going to take this thing and move it over here. Right? It's simple, just 3 steps. Did I have to shift over suppose that there were 1 million elements in this thing, right? Did I have to shift them all over? No. All I had to do was create a new node, make it point to this one, and make that one point to that one. Right? Only 3 operations instead of 1 million operations to make room for it. Right? Now this seems like a great solution. So why didn't we just go with this one to begin with? Well, what happens if you need to insert it at an arbitrary middle location here, right? Or at the end? Now, to be able to even get to there, you have to start at the head and go next, 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 all the way to the end in order to get to the tail here. Right? In other words, there are trade-offs. What was efficient with an array-based list is now inefficient with a linked list, and vice versa. What was inefficient with an array-based list is now efficient with a linked list. They both have their applications. They both have the appropriate situations where you would want to use one or the other. What I want to do for the remainder of the day and probably this week is implement a linked list. Right? Again, it works by linking one node to the next in what we call this chaining. Right? It's basically a chain. Right? Because they're linked together. Right? And as I depicted, the first node is called the head of the list. The last node is the tail of the list, right? There is no array, right? So, as a consequence, there is no random access, right? In other words, getting to the ith element costs you I operations, which did not cost us before. Like I said, to insert it at the last location, you'd have to start at the head, and then you'd have to traverse all the way to the end in order to get there, right? In order to be able to do that, right? All right, so let's go ahead and design and implement it. So design, implementation, and testing. Okay. Let me come over here to our IDE. I'm going to go ahead and get rid of all this. Maybe I want the demo there or whatever. But let's go ahead and create a new class called myLinkedList. MyLinkedList. Oops. Linked list. Now, I'm immediately going to start off with polymorphism here. I'm not going to make the same mistake that I did before and design it only for integers in order to make it more generic and parameterize it. I'm going to parameterize it from the beginning. Okay? All right. Now, there is no array, so I'm not going to be holding, say, an array of elements of type T here. Right? Instead, what am I going to be holding? Right? The only thing that I hold is a reference to the head. Okay, I'm going to make that private. And what type is this? All right, let me come back over here to our depiction. The head is referencing a node. Right? The node contains two elements. The element that is being stored here, and then a reference to the next element. So let's go back to object-oriented programming. Anytime that you have two or more pieces of data that need to be logically connected together, what should you be doing? Creating a class, right? And that's what we're going to do first. It's going to be our node class. Right? New class. And again, I'm going to parameterize this. Node of an element of type T. Okay? That node is going to hold two things. One is the element, so let's make it private. Element of type T, and I'll just call it item or element, whatever you want to call it. Let's call it element, right? And then a reference to the next node. Well, what is that next node? It's a node. And that node is parameterized to hold similar elements. So you don't have a node here with a string, and then it's pointing to a next node that is an integer, and then the next node is a double, right? They all have to be the same thing. Okay? Awesome. That's all we need. Now we also need getters, setters, if we're so inclined. We would need a constructor. We would maybe need a toString method, et cetera, et cetera, et cetera, right? But we'll come back and we'll worry about that later, okay? Now that I have my node class, what is my head? It's a node of elements of type T. The same parameterization as my linked list up here, okay? Cool, that's all. Right? You're only keeping track of one node. You're not keeping track of them all. That would be an array list, right? Then you'd be back at square one where we were prior to the break. Right? Now, what goes into my linked list right now? What else would you want here? Well, certainly you would want what? A constructor, my linked list, linked list. There we go. And the default constructor here will just set head equal to null, right? In other words, it creates an empty list, okay? What else would you want to put in this my linked list here? Well, let's come back over to our design principles for an array-based list, right? What do we need? We need a way to create stuff, retrieve stuff, update stuff, and delete stuff. I already designed that interface though, didn't I? We designed it with respect to a my array list, right? We have a method here that adds an element. Right? If you just look at the method name, add element, and it's a void function, right? Does it tell you that it was being stored in a node? Does it tell you that it was being stored in an array? Neither. Right? I want that one. I want that method in my linked list as well. I want that method in my linked list. I want that method in my linked list. But the implementation is going to be different. Okay? So now, if you have two very, very similar classes with the same interface, right, but different implementations, specific behavior over here that stores everything in an array list or in an array, and everything over here in a linked list, right, a bunch of nodes, right, then what should you do? Inheritance. Right? So the first thing I want to do is think about, well, what unifies these two things together? Let me go ahead and create a new class. Right? In fact, it's not going to be a class, it'll be an interface. Let me go ahead and right-click, new interface. Maybe we have reason to make it into a class later on, but I'm going to make it into an interface for now. My list of elements of type T. Right? If I just think of it as a generic list, it's not a linked list, it's not an array list, then what is its interface? What are its publicly facing functions? Right? And I've already identified those when we went through this, this exercise with the array-based list. I want a way to add elements. So let me go ahead and grab all of this and move it over to my list. Right? That's where the documentation goes to. Now, is there an implementation here? No, because it's an interface. It's a pure abstraction. This is an abstract method. I don't know how it adds elements, right? If it's stored in an array, then it would be one way. If it's stored in a node, it would be a different way. Right? Likewise, I'm going to take over here and grab add element at a particular index. Right? Indexing still makes sense in the context of a linked list. It's just that you don't have random access. You can't jump to the ith location by a simple memory offset. In order to get there, you have to start at the head and go next, 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 next until you get there. Add element, add element. What else do we want? Let's come over here. And I want a way to retrieve elements. Give me the element at the ith index. There we go. Right. Next one that I would want is, again, CRUD, create, retrieve, update. So update element at a particular index. There we go. Just the interface though, not the actual implementation. And then finally, the other publicly facing method, the last one here that I'll do, because the rest of them are all helper methods, which are all private, right, is going to be remove element. Right? And then it returns the element at that particular index. That is a great start on my interface. Now what I can do is I can come over here to my integer array list, and I can, or my array list, excuse me, and I can say that it implements that interface, my list of elements of type T. Right? And it already does, because that's where I got all those methods from, all those method signatures. I don't have to do anything else special to this class. But what I do have to do special now is my linked list class. Right? I'm going to make this implements the same interface. Now, I'm going to go ahead and generate all this stuff. Let's go ahead and add unimplemented methods. There we go. There. A bunch of to-dos, and that's what we're going to have to do next, right? But otherwise, now they are unified under this one interface. If we want to, we can go ahead and highlight them all. My array list, my linked list, and my list. And let's take a look at what it looks like as far as a UML diagram goes. All right, redo it. There we go. There. Now I'm using inheritance, right? And I've got it. Now I've got it all unified. Now over in my demo, I can use the same polymorphic behavior to say that this is not an array list necessarily. It's my list, right? Now this particular implementation implements that interface, but of course I could always change that to my linked list. Right? And none of the code changes. Right? So you want to now, by the way, this is going to end up being really, really efficient now. Right? I can insert a million things in the matter of a few seconds, a few minutes maybe, because my computer is kind of slow. But I, of course, need to implement it first. All right? All right, with the rest of our time, let's go ahead and try to do as much as we can. Okay? All right, add element. Now this adds it at the end of the list. So how would you go about implementing this? So this adds the element at the end of the list. So, you know, how did we do it in the array list? We cheated, right? Cheated. How did we cheat? We called that other method. I like that. Let's go ahead and steal that and put it over here. Right? Now, the array-based list, that kept track of the size. Maybe we should do the same thing here. So I have a reason to redesign this a little bit. Right? Let's go ahead and add in private int size. Right? Okay. And then this dot size is equal to 0 initially. Oops. There we go. This dot head. Okay. Now wait a second, I've repeated myself. I've violated the DRY principle. This method is exactly the same in both of these classes. When you have a method that is exactly the same in two subclasses, that is your strong hint that you should be promoting that up to the superclass to be able, so you have one implementation, right? And not these two different implementations. Can I do that? Let me go over to my list and see if I can implement it that way. There we go. And let's go over to my list. Add element. Can I give this a body? And say add element? No, because it doesn't know anything about this dot size. Right? Well, that's another redundancy. Over in my array list, I have a size, and in my my linked list, I also have a size. What else should I do? Promote that up to the superclass. Right? So both of those should have a size. I'll make it private initially, int size. Right? Now you can't do that in an interface, right? Because an interface is a pure abstraction. It doesn't have, it has default methods in later Javas, but everything should be abstract. It doesn't have any state. So it's not an interface that I want anymore. What is it? I want something, interface was a super abstract. Then down here I've got actual concrete classes. There's something in between. What is that something in between? You're using it in your, hopefully you're using it in your project right now. No? All right, big time points off if you're not doing something like it. All right? So what is it? What is between an interface and a class? No? An abstract class. Right? Everybody should have this, right? If you don't have this, then you're probably doing something wrong, right? All right, so we have an abstract class between them, right? Now we can have a size. Now we can have a default implementation here. And I can take out those redundancies now. I don't need this repeated because it's inherited from the superclass. I don't need this size here because it's also implemented from the superclass, right? And I do need to change some things around here because I can't say this dot size. Instead, I need a new keyword here, protected. Right? Now, protected allows the subclasses to see that variable, right? And in this, so it's a little bit less restrictive than private, but you certainly still don't want to make this public, right? Now everybody can see that, including the subclasses and outside the class. So I'm going to make this protected so that the subclass can actually see it. Okay. What else needs to be changed over here? Oh yeah, it's not. Let's see. I would need to label these all as abstract, right? Because it's no longer an interface. So abstract. There we go. And then I don't have to give it a default behavior there, an implementation. Abstract, abstract, and abstract. There. Now it's an abstract class. Let's come over here. Let's see. Oh, and then it's no longer implements my list. What's the other keyword there to make it a subclass? Extends. There. And that's the only thing I had to fix there. I've removed all the redundancies though. Okay. Now let's come, I've not, no, actually there are still a couple of redundancies that I need to take care of, but we'll take care of those as they pop up. Okay. All right. So I need to get rid of that redundancy right there and we're all good. Right? Oh, and then it's no longer implements my list. It extends my list and that takes care of everything. Now let's take a look at what the UML diagram looks like now. My list, my linked list, and my integer array, or my array list. Right, there we go. Now I've got solid arrows going up indicating that it is inheriting instead of implementing. Right? And I don't see any immediate redundancies anymore. Okay. All right, cool. So add element. Now we need to add it to the arbitrary index here. Okay. What could we get done though? We've only got 10 minutes here, so let's do the easy one first. get an element at a particular index. So what's the first thing I should do here? I want the ith element, or the indexed element. Right? You got to make sure that that index is in bounds. If the index is less than 0, or the index is greater than this size, then it's invalid. I would throw a new runtime exception, right? Invalid index plus index. Right? Actually, it should be greater than, or there are 5 elements in there. 0, 1, 2, 3, 4 is okay, but is 5 okay? Nope. So we'll throw that exception there. All right. But now, how do I get to that index? I don't have an underlying array, this dot array of index, because there is no array anymore. This is a linked list. So how do we get to that ith element? Right? Well, let's look at an example. Suppose that I wanted to get to this element right here. In other words, this is going to be 0, 1, 2, and 3. I need to get to that element in order to return 30. I only have access to the head. Right? So that's where I start. Then I go next. Then I go next. Then I go next. At that point, I have access to that element, and then I return it. Right? How many times did I go next, next, next? 1, 2, 3. Right? In other words, the same number of times as you would ask for the index. If you asked for index 0, how many times would I go next? 0. Right? I wouldn't go next. Right? All right, let's figure that out then. Right? Basically, I'm no longer, jumping to a location. I'm going to the first one, then the next one, then the next one, then the next one. In other words, I need to keep track of where I'm walking. If there was a person that was traversing this as a list, they'd be standing on top of this one, then they'd step to the next one. Then they'd step to the next one. They'd step to the next one. But they always need to keep track of where they are. In other words, the current node. So let me go ahead and give myself a current node. Node of element type T, current. Right? Where do I start? Well, where's the only place that you can start? At the head. Right? All right, so my current node will be this dot head. Right? Now I want to go next, 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 next. How many times? That many times. Right? So we can use a traditional for loop here. For int I equals 0, I is less than index I plus plus. Right? Traverse to the next node. Right? How am I going to do that? Current is equal to currents next, right? Well, okay, at this point now I need to go back and start actually implementing this node class a little bit more. First of all, I need a constructor, right? So let's go ahead and go up to source. I don't like typing, so I'm going to go ahead and generate a constructor using fields. And I don't have a next here immediately, so I'll just go ahead and generate it using element. There we go. Reformat that a little bit better. There we go. And this dot next is equal to null. Now, that's going to happen anyway because the default value of a variable is going to be null, but I'm going to set it explicitly to null here because I want to make sure that I'm writing intentional code. That I'm sending a signal to whoever reads this that, yes, I know that it needs to be set to null, so I'm going to explicitly set it equal to null. We're also going to have some getters and setters maybe. Source. Let's just go ahead and generate getters at first. So let's select our getters. Right? Generate those. And now you can get the next. Right? And it returns a node of element of type T. And so I can replace this with current.getNext. There. So the current will be updated to the next, then to the next, then to the next, then to the next, then to the next, for however many times you need to do it. At that point, you are now standing on the node that you want, 30 or 40 or whatever. And we'll go ahead and return current dot get element. Right? All we're doing is extracting the element out of that node and returning it to get that element. Right? Okay. Now there's no way to test this yet because of course there's no way to get stuff into there yet, right? We haven't done the add element, we haven't done the update element, we haven't done the remove element. And so we're not going to be able to test this just yet. But we could try to, no, it'd be too much. I could try to construct this manually by creating a bunch of nodes, 10, 20, 30, 40, 50, and then stringing them all together, and that's my list, but I don't want to do that. Instead, what I'll do is I'll wait till next time so that we can actually implement this and see if it works. All right? Let's outline it at least with a few minutes left here. So add element at a particular index. How's that going to work? What's the first thing that we should be doing in all of these? Check bounds, right? In other words, is that index correct or not? Like if there are only 5 elements and you want to insert it at 1 million or -5, we're going to throw an exception on that, right? Otherwise, we'll find the node at which we want to insert the element, right? Then 3, we'll create a new node, right? And we'll change our references, right? What we'll do is we'll make the previous node point to the new node, and then we'll make the new node point to the next node. Right? And we'll visualize that all later on. Anything else? Step 6, question mark, question mark. You're going to help me with it next time. All right? All right, any questions on linked lists so far? No? So remember this week, your labs will continue on JDBC. You'll have a lab on linked lists next week. But then at the end of this week, your database is due. So that includes your database, design and implementation. That includes an ER diagram that has to be handed in, and that includes a list of like 12 queries, SQL queries that you have to use to test your database, basically. And that's all due on this Friday. We should have our feedback back to you on your design documents, including your database design, by Tuesday, or tomorrow sometime. All right, I'll see you on Wednesday then.